Group 11 from section 1, and we're about to report the voltage reference band gap circuit. So general use or ideal voltage reference voltage is a circuit used to generate a fixed voltage, which is the Vref, that is independent of the power supply voltage or the VDD, temperature and process variations, where Vref is less than VDD. In other words, the ideal reference voltage is independent of PVT. For example, if Vref increases with temperature, we say the reference voltage is proportional to absolute temperature or Ptat. If the reference voltage decreases with increasing temperature, the reference is said to be complementary to absolute temperature or Ctat. Both Ptat and Ctat references can be used to design a voltage reference that changes very little with temperature, called a band gap reference. MOSFET resistor voltage references uses voltage divider formed with two resistor that has the advantage of simplicity, temperature insensitivity, and process insensitivity. That is, changes in the sheet resistance have no effect on the voltage division. The main problem with this circuit is that in order to reduce the power dissipation, the resistors must be large. MOSFET resistor reference. The reference voltage used in the resistor MOSFET divider is equal to the VGS of the MOSFET. Equations written on the slide, if Vref is designed so that it is close to VTHN, then the reference voltage will be insensitive to changes in VDD, and its temperature behavior will follow the threshold voltage. However, for the general case, the temperature coefficient of the resistor MOSFET voltage divider is determined using the other formula.
The temperature coefficient of the resistor MOSFET voltage divider is determined using the first equation. If we assume VDD is way much higher than Vref, we will have the equation shown. In this example, we estimate the temperature performance of the resistor MOSFET voltage reference seen in the figure. We assume that the circuit has the following parameters. For the reference made using the 1 meg resistor, the current that flows in the circuit is shown in the first equation, which can be solved to determine current is around 4 microampere and Vref is equal to 900 millivolts. The rate the threshold voltage changes with temperature is shown in the equation 1. The temperature coefficient of voltage reference is shown in the equation below. We assume that the threshold voltage was measured at 25 degrees Celsius. The simulation results are here. At higher temperatures, the threshold voltage decreases and so does Vref. The change in temperature of 25 degrees Celsius corresponds to the change in the reference voltage of 31.25 millivolts.
The MOSFET only voltage divider. The MOSFET only voltage divider generates a reference voltage that is equal to the voltage on the gates of the MOSFETs with respect to ground. Since ID1 is equal to ID2, we can assume that beta 1 divided by 2 multiplied to the square of the change in voltage from VTHN to V reference is equal to beta 2 divided by 2 times the square of the differences in the voltage of VDD, Vref, and VTHP, where the reference voltage is given by Vref is equal to VDD minus VTHP plus the ratio between beta 1 and beta 2 times the voltage in VTHN all over the ratio of beta 1 over beta 2 plus 1. or knowing the desired reference voltage and power supply voltage, we have an equation: beta 1 over beta 2 is equal to VDD minus Vref minus VTHP all over Vref minus VTHF quantity squared. The temperature coefficient. Assuming the temperature dependence of the ratio of the transconductance parameters is beta 1 over beta 2 is negligible, is given by the TCV reference is equal to 1 over voltage reference times the change in voltage reference with respect to the change in temperature, equal to 1 over voltage reference times 1 over the ratio of the square root of beta 1 over beta 2 plus 1 times the negative change in voltage in VTHP with respect to the change in temperature plus the square root of the ratio of beta 1 over beta 2 times the change in voltage of VTHN with respect to the change in temperature. We can determine the change in voltage with respect to the change in temperature by the given equation for long channel devices such as change in voltage over the change in temperature equal to negative 1 millivolt per degree Celsius, and negative change in voltage over the change in temperature is equal to 1.4 millivolt per degree Celsius. To achieve zero value for TCV reference, it requires that the negative change in voltage with respect to change in temperature is equal to the negative square root of the ratio of beta 1 over beta 2 times the change in temperature over the change in voltage over change in temperature. It will be equal to 1.4 millivolt per degree Celsius, which is equal to the ratio of the square root of beta 1 over beta 2 times 1 millivolt per degree Celsius, or simply the ratio beta 1 over beta 2 square root equal to 1.4. For our LT spice, in our example, we made use of the LT1635, which ensures an output voltage as low as 0.2 for the reference voltage, which is required to V minus and referred to as V minus, and includes buffer amplifier to enhance flexibility. The reference and buffer combine to achieve a drift of 30 ppm per degree Celsius, a line regulation of 20 ppm per volt, and a load regulation of 100 ppm per milliampere. It is connected to a 5.5 volt source, which is required based on the spec sheet. As we can see, the voltage in the reading is as low as 0.6 volts, and it's up to 1.2 volts. And that ends our presentation.